a special role for strongly coupled nuclei. Dense concentration and strongly coupled nuclei, pretty much we're talking about protons. And their behavior is qualitatively different than the behavior of a rare uncoupled spin, like an isolated C13 in a selectively labeled sample. If you have a dense collection of protons, one relaxation process at one location in the protein, because of spin diffusion, can effectively relax all protons in the solid. There's some truth to that statement for solution NMR, but it's an extremely good picture for solid state NMR. So usually we just don't worry whether we're going to have a proton T1 mechanism or not. If there's a methyl group, for example, in your sample, you're going to have a T1 mechanism for your protons. If you were to do direct detection on carbon, however, the same statement does not hold. Some of the carbons in your spectrum will require minutes to recover back to Boltzmann. Some will recover quickly. So you'll definitely get a distorted spectrum if you repeat rapidly. So protons, X nuclei, kind of different. That's to some degree also true in solution, but it's a very clear picture for solids. Now there are lots of kinds of relaxation. T1 relaxation is not the only relaxation. This is, again, same in solution versus solids. So you might set up some other coherence, not just C magnetization, but like a double quantum coherence or a zero quantum coherence. And if it's longitudinal, it's analogous to a T1 measurement, but the rate constant will not be the same, be different theory, different measurements. So it's a general or flexible concept. It fits into this course also because we do happen to be interested in protein dynamics. And so we want to understand the quantitative relationship between conformation exchange and the rate measurement of relaxation. Very parallel to solution, same thing Art already said. And even the physical picture we'll use will be similar between solid state relaxation equations and solution. So everything Art said about solution NMR relaxation theory is relevant to solid state. I think that the most important assumption when you want to apply Redfield theory, if that's the way you're going to think about relaxation, the most important assumption is that the motions you are studying are fast, and they're faster than a lot of things, but the best way to say it, I mean, a lot of ways to say how fast do they have to be, but this is the most general. The rate of change of the magnetization that you're talking about in your theory, T1 here, and the rate of change of any coherent convolution sets a time scale, defines a time scale, which for us is usually microseconds. For solution NMR, it might be more like milliseconds. Your rate has to be really fast compared to that, or most of what we did with that theory derivation earlier this week won't be correct. But if you can make that physical assumption, that's the fast limit or weak field limit, then there's a theory and a quantitative expression. This is totally the same story for solution and solid state, so we won't repeat it. Then another thing which is the same is these equations are good for predicting T1. If you have a specific model, how big is your CSA? What is tau C? What is the angle? If you can tell me all those things, we can put them together into a computer and you can predict T1. But if you have T1 that you measured, you might not have a unique interpretation. All of these statements are really the same for solution and solid state. People work very hard on this. If they have a large number of measurements, can they at least say something about their interpretation? Big activity area for biophysical magnetic resonance. One more parallel, I skipped over it. The T1 minimum. Do you know that phrase, T1 minimum? This is a phrase you'll see more often for solution NMR than solid state NMR, but the concept is the same. When the fluctuations are about the same as the Larmor frequency, you get the strongest T1 mechanism. It's like almost on-resonant fluctuation. the movement of the molecule is resonant with the RF, or with the levels for the nucleus. Funny idea. So if you're on a 360 megahertz instrument, that would be a time constant of about 3 times 10 to the 10, minus 10. If you're on a really low field instrument, it might be more like 10 to the minus 9. If you're up on a 900, it would be closer to between 10 to the minus 10th and 10 to the minus 11th. So the T1 minimum refers to the rate of fluctuation of the molecule that would give you the most powerful T1 mechanism. If you can change the temperature, you can change tau C. And you can figure out whether you're basically here, slower than the Larmor frequency, or here, faster than the Larmor frequency. So you change the temperature, and conceivably, as you get colder, you might get more relaxation, or as you get colder, you might get less relaxation. It depends which side of the T1 minimum you are. So that's a useful thing to be aware of. And by the way, the same picture does not hold for T2. We're going to talk about that T1 minimum picture more later, I hope. But it's a useful concept, and you'll see this phrase in the literature sometimes, T1 minimum. Solution NMR, what would you think the tumbling time of your molecule usually is? Let's say you had a ubiquitin or some larger protein. What do you think tau C for the overall tumbling of the molecule is? Say it. Maybe 1 nanosecond, maybe 10. So where are we here? We're here someplace. So you're right at the T1 minimum for old-fashioned, low-field instruments. What about a water molecule, like a small molecule? What do you think tau C is? Picosecond. If it's an organic compound in a non-viscous solvent like chloroform, excuse me, maybe 10 picoseconds. So picosecond is way over here. So you're in a very different regime compared to the T1 minimum. But remember that the T1 minimum would be more like here for a modern instrument. This is an old slot. We just took it from an old clock that I have. So low field instruments. Now, the most important thing for this class on this slide is in bold, that we think that we can get information from studying T1 in detail. Some of the other things here are sort of general NMR background, introductory comments, but the section that Art taught has to do with connecting the relaxation you measure to a model for motion. And people show this all the time, the idea that you can probe motions on lots of different time scales. The tumbling of the molecule is about this fast if you're in solution. The bond vibrations, domain motions, enzyme catalysis, these things are slower, bond vibrations are faster, protein folding would be slower. For each of these time constants, you have a different NMR experiment. So we're talking about this experiment right now, but later on we'll talk about other experiments. Now, this experiment is right on the right time scale to study the tumbling of the molecule. It's the same thing we saw in the last graph. It's the right time scale to study the methyl group rotation. Those happen to be also usually about a nanosecond. Methyl groups, the 3-site hop. Like if I have 3 proteins in a methyl group, I can propose that maybe thermally, because of collisions with other molecules, it will interchange and become here. And what is the typical time constant? Well, it depends on the environment, but it's about a nanosecond also. So these are 2 things. Tumbling of a small protein methyl group, those things really give you relaxation. But there are some other possibilities also, maybe very fast local flexibility in your protein. Matches the time scale of spin lattice relaxation at mid-field 600 megahertz and high field 900 megahertz magnets. Now I'm going to say the same thing with another way to depict it. This is now in a table. So when we talk about fast regime in NMR, we're usually talking about picoseconds to nanoseconds. And what makes us say that that's fast is that the time constant is much less than frequency differences. It's even less than the Larmor frequency itself, but it's certainly faster than differences in frequency within your spectrum when you undergo conformation exchange. Such fast motions can drive relaxation, and I'm also going to mention that they reduce what you think the tensors are. The dipole coupling, the CSA, will look smaller because of fast motions, artificially smaller. That's by contrast with intermediate exchange or slow or ultra slow regimes, which we'll talk about separately later. Start with the fastest. The picture that we would use to make a theory, again, it's the same, solids versus solutions. It begins by separating the Hamiltonian. So you have time-independent large piece, usually large, and you have a fluctuating piece, H0 and H1. And actually the magnetization follows the total Hamiltonian, H0 plus H1. But we're going to think about them as being different in the following respect. This is for coherent evolution, and if we want to study relaxation, we should remove it with a frame transformation. This is fluctuations. Why is it fluctuating? Because the molecule is moving. That's what we're going to study, the fluctuations in the Hamiltonian. But all we can really measure is the relaxation of the spins. So it's an indirect way to study the fluctuation in the Hamiltonian. So you begin by separating it into a fluctuating piece and a constant piece. You make a frame transformation, and now in that new frame, transformed around H0, you're going to study the evolution due to H1. Well, the problem with H1 is it's not constant. So your first guess is to take the average. So, well, what's the average of H1? Well, the whole way we constructed this, the average of H1 is 0. So the first order picture is that there will never be any relaxation. It's 0. So that's why you were discussing with Art yesterday a second order piece where you take the effect of this fluctuating Hamiltonian on the initial density matrix, and we're assuming it's not an equilibrium or there would be nothing to study, so the initial density matrix is not the same as the equilibrium, and I'm going to take the commutator of that with respect to the initial value of the perturbing Hamiltonian, the fluctuating Hamiltonian. And if that's all I study, I know I'm going to get 0, so now I take a second commutator. This is totally analogous to that expansion we talked about before. We're looking at approximate values of time-dependent Hamiltonians during magic angle spinning. We said there's sometimes you have terms in the Hamiltonian where time dependence is so complicated, let's just study the average. But if the average isn't a good enough approximation, we're going to have to take a second order term. If you look back in your notes from that section of the class, we're doing exactly the same thing here. The only difference is back then it was a sinusoidal variation because of magic angle spinning. Over here, nature, temperature, collisions with other molecules, it's a chaotic and random fluctuation. It's an important difference, but like the formalism we're doing is the same. So that's what Art already talked to you about. And then the next step is always to think about the Hamiltonian as having spin versus spatial degrees of freedom. So these Hamiltonian H1, you're going to think about the spin operators, and you're going to think about the spatial degrees of freedom. The spatial degrees of freedom are how you learn about the molecule. The spin operators tells you which transitions you can study. Pull out the spin operators and you find out which transitions you're measuring in terms of the relaxation. Every one of those transitions has its own projected spectral density and spatial degrees of freedom. This picture is the same. Solution solid state. This is I may be saying it differently, but I'm describing exactly the same thing. So the spatial degrees of freedom is the molecular information, this bit out here. And you can also say, well, let's make a distinction between the time dependence of J, the time dependence, and that's how fast this fluctuates, how fast the molecule moves, how long do we have to wait, T prime, to get this term to move. Is it characteristically a millisecond or a picosecond? And then it has an amplitude. How strong is the interaction? And remember, it's not the complete interaction, it's only the time-varying piece. So let's say I had a little bond vector, NH. You guys thought very hard recently about how strong is the dipole coupling in the CSA for an NH vector, okay? So you've got an equation for that. But let's say it only moves this much. It's only moving in 5 degrees angle. A lot of that coupling would be in H0. It's only moving a little bit, so there's part of it, part of the coupling is the time varying piece, is the difference between its value at this angle and the value at this angle. So you take P2 cos theta 1 minus P2 cos theta 2, that is H1. H0 is all the rest of the coupling. So the size of this is usually going to depend on like the angle or how much the environment is changing, if the isotropic shift also changes. The time dependence is a separate concept, and it's really separated nicely by doing the spectral density function. So you'll have some amplitude for the spectral density function. The largest amplitude it has is always at the lowest frequency. And then the characteristic time constant for the motion, well, that has to do with how does the spectral density change with frequency. If it's a very fast motion, it's pretty flat until you get out to higher frequencies. If it's a slower motion, then the spectral density will be a strong function of frequency even at low frequencies. So the time, tau c, and the amplitude, two totally different pieces of information that sit in that spectral density function. That's the same for solution, that's the same for solids. No difference. I'm just recapping with slightly different words. And as I mentioned, when we talk about the spatial degrees of freedom, we're going to be using spherical harmonics, all that stuff that we learned before. That's what we use to describe the amplitude of the motion. We'll use spherical harmonics, but we won't do very much of that today. Today we're going to talk about some qualitative features. So from that theory that Art presented and that I was just reminding you a little bit about, you can derive expressions for R1 and R2 assuming different kinds of interactions. So R1 always means that I'm measuring the Z magnetization, not the double quantum, not the zero quantum, but just the single quantum Z magnetization. But I also have to specify what interaction I'm modulating. And if I'm modulating the dipole coupling, I get a different expression than if I'm modulating the chemical shielding interaction. Each of these expressions has a strength that has to do with the strength of that particular coupling, how large the difference in omega is when I undergo the motion. And each of these terms has a spectral density function, and that's what's going to be dependent on the time of the motion. This is a really simple approximation for the spectral density function. I used it when I made the plots on the previous graph. That the spectral density function, if it's a random process, totally random, no memory. So in other words, I got kicked by a molecule, but by the time I have time to think about it, that molecule's gone and I've got all sorts of fresh molecules in. I cannot remember my history. Okay, that's the physical assumption. Then you would expect the correlation function to drop off as an exponential, and that means that the spectral density has a Lorentzian type line shape, this function. So when we don't know anything about a system and we just have to make a dumb guess, we always use this expression for our spectral density. I'm not of the opinion that it's always correct. For polymers or biopolymers, there are definitely cases where this isn't the right function. But We use it because it's a simple function, and it will be correct some of the time. So if you use that function, you can predict things like this T1 minimum and so on. That shows you quantitatively that J of omega is highest when this is about 1. The product of omega naught and tau c is about 1. That is the maximum of this function. And that's why we have these T1 minimum. So these expressions give you qualitative insights like that you know that there's a T1 minimum. And they might give you quantitative insights for a very specific amide. Let's say you go and you measure T1 for some amide in ACSA or some other protein. This is the kind of expression you would use to say, what does this T1 mean? But as you can see, you'll want to measure the T1 at more than one temperature. Otherwise, you don't know whether the right answer is this one or this one. And ideally, you'll want to measure it at another magnetic field and some maybe other experiments so that you're really confident with what you're saying with your model. Normally, we don't just have CSA or dipole. Normally, we have both. So you might also think about an expression for relaxation, R1, when you have both. But you remember Art was talking about it. You have to decide whether these are correlated or not. The CSA and the dipolar. It's like a model where you add those two tensors before you consider motion. But they need to be added, and then motion moves them in a synchronous sense. That's referred to sometimes as cross-correlation. So this expression doesn't consider cross-correlation. It's just adding up what you expect from the dipole plus what you expect from the chemical shift. It's just adding them together without thinking about how to make them correlate. Besides CSA and dipolar, there are other mechanisms for relaxation. Can you think of one? And maybe other terms that we should add. Anything else in the Hamiltonian that we should add? The quadruple, when you add the quadruple? For spin 1, so if you're doing deuterium, nobody does N14, but it's a big, wide open frontier for people in biophysics. That's an NMR active nucleus that's in there in your protein. It's just really difficult spectroscopy. What else besides quadruple, dipole, CSA? If you had a paramagnetic center. All right. That's a bit of review where I emphasize what is the same in solids and solution. Now I want to talk about what's different. So I'm just taking a pause to see if you have a question or two, a comment, or something you want to hear more about today or another time. I didn't redo all that derivation. Sometimes the best thing is for you to do that by yourself and find a question. You just keep hearing other people say it, it doesn't get any better. But if you sit at your desk and you try to derive it, you'll have a very smart question, I'm sure. So, do you want to hear about the differences or do you want to ask a question? Go ahead. All right, the first thing is what Art already mentioned. A big part of interpreting the data for solution NMR is the overall tumbling. Because that overall tumbling is exactly at the right frequency to give you a maximum effect. So when you see a T1 value or an R1 rate for solution NMR, you can assume that almost all of it is due to overall tumbling. And that the internal motions we're so interested in are a small correction of tumbling. That's really interesting. And we, in solids, we're not going to have overall tumbling. So everything we measure is due to internal motions. But I want to point out that there are some interesting papers from Martin Blackledge and Lyndon Emsley where they talk about the fact that there is a little bit of overall tumbling in solids. Like in a protein crystal. People like Greg Petsko, he's a famous crystallographer, studied the rocking of protein inside the crystal. Imagine that the protein has a neighbor here and a neighbor here and a neighbor here. So it has some hydrogen bonds. Usually it still can wiggle a little bit. Will move the parts that are least contact area, least energy of contact, but it will wiggle a little bit. So he fit his X-ray density, especially the disorder in his electron density, to claim that there's a kind of rocking motion inside the crystal. So Emsley, Blackledge, and others talked about that as being a T1 mechanism for solids. Very interesting comment. If that were the right mechanism, you would expect some pattern where you'd have patches that have very little T1 and other patches where there's lots of T1, where the rocking is pivoting on one point. I'm not sure it's all that clear, but conceptually it's very clear, but I'm not sure it's all that clear in the data how much of that really is. The other thing is, since there's no overall tumbling, we'll expect this idea of the T1 minimum to be a little more powerful. The entire effect is due to an internal motion. So you really can do this experiment where you start at cold temperature, medium temperature, hot temperature, try to find your T1 minimum. It's very nice because otherwise you're interpreting one relaxation rate and you have a lot of adjustable parameters and you will never feel that your fit was unique. But if you can vary the temperature and find the T1 minimum, there's something you really know about your motion. And you don't really have that in solution because you can't vary the temperature and because anyway you're studying tumbling most of the time. So this T1 minimum is brilliant as long as you think that the same processes go on over a broad range of temperature. So let's have an example. If you're studying a methyl-3 cycle, it seems to me like it's likely that you could really vary the temperature from 100 K to room temperature, and it's probably that same 3 cycle. It's probably okay. So we did some work on that. Lots of people have done some work on that. If you're studying the opening and closing of an enzyme, I think when you freeze the solvent, it's probably going to be just a qualitatively different process. So it's probably not a good idea to do high temperature, medium temperature, low temperature, and like assume that you can use Arrhenius processes and the whole thing is the same process. So anything that would be affected by the solvent freezing may not work as well as I said, right? Or lipid dynamics, and they have a phase transition. You can't really join all those data sets and assume that they describe the same process. It might be qualitatively different after a phase transition. But for some cases, it's a big opportunity. Now, another difference between solids and solution, when we use the word order parameter, we might mean something different. For solution, as Art elaborated yesterday and last week, the order parameter basically describes the motions that are faster than overall tumbling. We don't have overall tumbling, so we don't think this way. We think about the motions that average our tensor. And so it depends on which tensor. If it's a really broad tensor, fast motions only will average it. If it's a really narrow tensor, even slow motions might average it. So what is the time scale that we're thinking about when we have an order parameter? You have a vector which is moving, 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 and you're going to average the tensor over all these frames. How long do you have to average? You have to average until the number is stable. Well, when will that number become stable? It's to do with the comparison of the correlation time and the strength of the tensor, the time scale of the tensor. And so it depends on which tensor you measure. You had this as a problem in your problem set, in those homework problems. I said if a motion is much faster than the range of frequencies given by the local field. In other words, if your CSA is 10 kilohertz, suppose that your rate constant K is much, much greater than 10 kilohertz. You can predict what happens to the tensor width by doing an average like this, where you simply add up all the frames and then divide by the number of frames, and you'll have a new tensor which you might need to rediagonalize, but that is your average tensor, fast limit tensor. How long do you have to average? How many frames would you need in an MD simulation? It must be longer than 1 over the coupling. That's the rule. Longer than 1 over the coupling. I was before encouraging you to think about problems related to this, and I'm still encouraging you to do that. Averaging tensors, and you can think about this problem of how long do you have to average and when will it converge more carefully. All of this underlies the idea that the frequency is orientation dependent in your tensor, and it's an important concept for every interaction we work with, every single interaction. The first example of somebody measuring this kind of change in tensor that I'm aware of was done in David Grant's group by Kurt Zone and others. And what they did is they showed that the carbon CSA broad line spectrum, no magic angle spin, just static detected carbon, depends on temperature. And they could see the differences between 337, you see that edge there, and 295. So they're starting a little bit around room temperature and going up. And they could get rate constants from that, and angles were assumed from the molecular structure. So it's like a hop where this methyl group replaces this methyl group. I call those identity operations. You're just using the symmetry of the molecule. And from a chemical point of view, electron density point of view, nothing changes. After you make that molecule hop, you have the same structure. But if you are a spin and you're undergoing precession, when you hop over here, depending on the orientation of the crystallite, it could be a very different frequency. Right? Let's pretend, I should make this graphic. Let's pretend we put one of those molecules and put it here on the globe. That methyl group might be jumping from here to here. That would be a nice graphic to make this more clear. Okay, so you're averaging, and each crystallite will average differently. Each crystallite will average differently, and you end up with a new tensor. By the way, previously, we measured many of these tensors in ubiquity. What we decided to measure was not CSA, but CH dipole coupling. So Justin Loriot developed an experiment that was a derivative of an experiment already done by Mayhong, where he resolved all the carbons on ubiquitin and in another dimension measured their dipole coupling. And you could see, for example, two methyl groups in a rigid alanine versus a very, very mobile methionine, that the apparent tensor width is very different. And that gives you the angle of the cone that that CH group is sweeping out. Now, we express that angle of the cone with an order parameter, just like in solution. And it actually has the same definition. It's the average of P2 cos theta. You have an average value for your angle, and you're saying, well, all places I go, if I average them over time, but I don't want to average the angle, I want to average the interaction, so I will average this function. So I make a little movie of where my bond vector went, and at every interval, I record the answer to that question, what is P2 cos theta? I add them all up, and I average them. That is my order parameter. And they mean the same thing in solution. But it isn't the same thing because we have a different time scale we're going to average over. They're averaging up to the tumbling time. We're averaging forever, except that once you get much longer than the coupling width, it really doesn't make any difference, so you can stop there. So we tend to be measuring up to a microsecond, and they tend to be measuring up to a nanosecond. So in these early measurements, we noticed that our order parameters were lower, and we thought it was because the time scale is longer. So we're seeing more angles. But that was, in later years, we understood that that was only partly true. I mean, that is true, but I don't know how much it affects the data, because there's another effect that we should have used basically better decoupling in these sequences, and we would have gotten lower apparent dynamics or higher order parameter. So the difference between solution and solid state was partly a pulse sequence artifact and partly the longer time scale is probably the right thing. So that's fast limit motion. Fast limit motion changes the tensor. But fast motion also causes relaxation. So here's an experiment done not that long ago by Bob Vold and Gina Hodson, looking at a deuterium broadline spectrum. So no magic angle spinning. When I say broadline or static, I mean that there's no magic angle spinning. The molecule is not static. The the molecule is undergoing motion. This happens to be a methyl group. And so it has lots of motion. If I do an inversion and then detect, first the spectrum is upside down because I inverted it, and if I wait long enough, it's upright again. That is analogous to solution NMR, but it's different because I'm seeing a whole line shape at every time point. Now, we come to a really interesting difference between solid state relaxation and solution. I find it much more interesting than this business about the overall motion. Will every point in this line shape recover with the same rate constant? Not necessarily. If you look carefully here, there's these little horns. They're still upside down, but the edges have already recovered. We got interested in this effect a long time ago. So I'll show you some examples from our group, but first I'll just talk about why that's happening. It may be obvious to you already, but let's say the relaxation rate scales according to the frequency difference in the hop squared and the spectral density function. And the spectral density function, we can make some assumption that it's some simple thing. That's fine. Now here's the issue that I want to point out, is that the frequency change during the hop is orientation dependent. Remember that two-site hop for DMS, dimethyl sulfone. Let's say I put the dimethyl sulfone this way, it's going to be a huge hop in frequency space. Now let's say I take that same molecule and I place it like this. One methyl's here and one methyl's here. When I hop, nothing happens. Delta omega is 0. I think I really should make these pictures. I think it would help this lecture if I would actually make those pictures where I cut out DMS. So you see what I'm saying? You can have one molecule, one crystallite where it hops from here to here. Every time you undergo a hop, it's moving that much in frequency space. You can have another one where it just sits here and it doesn't even move. So each crystallite is a different story in terms of this, not this, but this. Could that give you some information? Absolutely. So I directed Jeff, you in particular, to a paper that Art and I wrote together when we were both assistant professors here on a paper with lots of ideas about what to do. And I think we never did any of the experiments we proposed. So you guys could do them still if you wanted to. But if you have different motions with different angles, you will get different fast limit spectrum. That's the averaging of the powder pattern. So it depends on the angle. But it's also true that if you propose different motions, you get different features at what we call the T1 crossing. That point where the integral of the whole signal is 0, but it's not actually flat, right? So on average, it's 0 here. Some parts are upside down, some are going up, but it's the closest to the 0 point that I can show you, right? I mean, that's basically the 0 point. What's the line shape? It's interesting. And it's not the same for different motions. So some motions, you'll end up positive in the middle, kind of. Other motions, it's really negative. It depends on the angle of the hop. And how many sites? Is it 3-site or 2-site? So in addition to this line shape, you have a whole other piece of information here that I can't look at it and tell you the angle, but if you use computer simulations, you can match the simulation to your data and figure out maybe what's going on with your molecule. It's really informative. So that's called anisotropic T1 or anisotropic T1 crossing. That the T1 time with a 0 crossing is angle dependent, so it's frequency dependent. It's very powerful. And people haven't used it enough. There aren't enough papers about this, especially in proteins. Here's something we did with one of my first students that I really enjoyed. You might have noticed in the Volt paper that the 0 crossing effect was kind of small. You had to really look at it. Bob Volt, I would say, always does things with amazing signal to noise. He collects the most beautiful spectra, so he can analyze these tiny little features. And I would rather try to find a system where I get a big effect, usually. So it's a difference in style. He's a very, very careful person. Anyway, here is, without scaling, this is like, you can see the noise is close to the same. A 0 crossing point high. Okay. I think you just finally got to the interesting part. It was all preamble until now. So here we are. This is a 0 crossing point for a inversion recovery of an amide where we had put a deuteron, where the hydrogen usually is an NH group, and we put a deuteron. What amide? It's a chemical compound. It's something from DuPont. It's not a protein. It's something where we could get a nice big signal. And we were interested in the question, when amides move from their favorite hydrogen bond, do they do this, do they do that, do they twist, so what are they doing? And we could put a deuteron at the CH position, and we could put a deuteron at the NH position, so we put them different places. This is the NH. And so that NH here, how does it rock? This is maybe the strongest interaction it has, but then rotating this bond has an energy barrier, so you could try to answer this with MD, but we tried to answer it by looking at the relaxation of the deuteron, invert it, and it begins to recover, and you can see that VZZ and VYY recover very rapidly compared to VXX. So the recovery time for VZZ is the very fastest. So on the basis of that, we propose that these motions, where basically have compensating twist along the chain, is a motion that had been proposed many times before, would probably be the main relaxation mode for the NH. That when the backbone of a protein is not fixed in space, that it would probably involve twisting on the flanking single bonds to produce a spectrum like that. But to be honest with you, we never got a spot on fit. There's no simulation on top of that because none of these modes reproduced the extent of the anisotropy. The shape was right, but the extent. So I could put a simulation here, and it would have these features that these are the highest. But this is such a large amount of anisotropy compared to those data from Boole on the Miller group. And I think the only right way to explain that is by proposing that it's not one time constant. There's a distributed dynamics feature. So those simulations became very complicated and underdetermined, and we ended up deciding not to put them in the paper. But basically, the mode has to be these twisting motions on the flanking groups. So you're like rocking a relatively rigid NH, breaking its hydrogen bond, forming it. And you probably are doing that in a diffusional way, not like a two-side hop, but diffusion with lots of rate constants. So that was a model compound, and it was already too complicated for us to do a quantitative simulation. But we did go on to show that you can see the same thing in protein motions. You can see these T1 anisotropy features. This is an example of a side chain on a loop of an enzyme, and this loop for catalysis has to open and close, and we were getting the rate constant from solution NMR, solid state NMR, FTIR, fluorescence, all kinds of measurements. And this is the solid state NMR. We did line shapes, which are not shown here, but here's our T1 measurements. The fact that the relaxation rate was so short, 100 milliseconds, could be fit to support our model for the motion. It's quite short, 100 milliseconds, 70 milliseconds. But the interesting thing is the fast limit motions depended a lot on whether we put a mimic for the substrate or the product or the intermediate, or whether we had an empty enzyme. So you get different zero crossings here. You can see that the shapes are different. And in the empty enzyme, there's an extensive disorder that's librational. It's just the ring going up and down would fit that line shape the best. And in the presence of the substrate, much less of that, just a large angle pop, but no diffusion motion. So you can see that the motion, characteristic motion, has different geometry. It's not that it has a different time constant, it's a different geometry at different points on the enzymatic cycle. So you can use these anisotropic T1 effects to constrain motion. But all the examples I showed you, this one from Vold, an experiment from Vold, these simulations of different angles, this small molecule that we studied to think about amide motions, and this loop. Every one of these examples to study the T1 anisotropy was broadline or static NMR. And there's been almost nothing done to take magic angle spinning and recover that kind of information. It's a big opportunity there for somebody who wants to do that. So magic angle spinning and T1 measurements has been done. So site resolved T1 measurements. You have a whole protein and you get, a plane, a correlation plane like your DAR spectra or like a DCP spectrum. So you have nitrogen-carbon correlation, and each peak is a different site on the protein, okay? And then as a third dimension, you just do T1. That experiment has been done for the first time by Cole and Torsha in '91, and they were studying staph nuclease, and they showed that the T1 was a pretty strong mechanism, even in a crystal, and then it depended on which amide. And they didn't do too much to interpret it, but it was a very important landmark experiment. And then there's been a lot of follow-up work. Lyndon Emsley, Martin Blackledge, Bert Wright, lots of people have done follow-up work where they measure T1 on the backbone of a protein, typically not able to give a unique interpretation. That's a typical case. But you can learn a lot about the motion, but to give a full interpretation is difficult. There's lots of effects going on. You could say that the internal modes of the protein that they're probing are reasonably similar to what was learned about the same protein by solution in the presence of the overall tone. That there are broad similarities where the loops are more mobile and that sort of thing. But none of these studies took explicit advantage of this anisotropic recovery. So that, like at the zero crossing point, you would have a very unusual set of crystallites contributing to your spectrum. In these experiments, even if you only had one motion, so you could have only one value for R1. Let's go back to that equation for a second. So there's just one motion. So there's a unique value for tau C. Doesn't mean you have one value of R1. So I'm studying a protein, I'm doing it by a solids NMR, I'm looking at the recovery of one particular amide, and I only have one motion, which is unrealistic, but we like to do this way. I have one internal motion. Should I get one value of R1? Should I fit it to a mono-exponential? No. It's going to be multi-exponential, and it's for the same reason, that different crystallites will have different delta omega. So another way of talking about this opportunity is that when you measure T1 by solids, MAS, you should expect to see more than one exponential in your curve fitting, even for a very simple motion. Even for one motion of one amide, one process. You should see markedly multi-exponential behavior. But I think most of the studies that have been presented, resolving those two exponentials and interpreting them has been sort of beyond the scope because there are just so many unknowns in the curve fitting and so many challenges with signal to noise. So that's an opportunity that's out there for somebody to look at the zero crossings and analyze the power, or to analyze the multi-exponential nature of the recovery. So these are features that you should expect in solids that you don't see in solution. And there should be information. Okay, so we talked about one difference to solution being that there's no tumbling. So it means that even though we have the same definition for the order parameter, in practice it's a different number. We talked about another difference being that relaxation is anisotropic. Each crystallite could have a different R1 value. And you can ignore it and get some qualitatively good information out, but maybe the best analysis to get the most unique information would embrace that and say, okay, why is this multi-exponential? What am I learning? The third difference to solution NMR that's important to keep in mind, I think the real motivator here is that we will be able to study different systems. And a good example of that from the literature is the very detailed studies of motions of lipids and liposomes done in a number of different labs. So membrane proteins in the presence of lipids, and not as much so far in terms of amyloids, but that will come. Some studies, a nice detailed study, little tiny amyloid from the Griffin group. So membrane proteins, amyloids, other structures like that. the backbone of capsids and other naturally occurring assemblies like cytoskeletal proteins. A little bit of that kind of work has been done by measuring tensors in the Ulanova group. So these kind of structures that you can't study by solution NMR, that's another big motivator. Now, I was thinking that Art was going to be here a while ago, and this is almost the end.
Just copying him, you know.
This is almost the end of my lecture. I just want to do one more thing, which is to talk about some sources that you could read more about this. Unlike the first section of my lecture, I don't have a handout for you that I typed up, but I'm going to talk about some sources. This is a recent review article from Paul Shanda and Matthias Ernst. I think that's a wonderful overview of some theoretical concepts as well as some experiments that have been done. And that's one paper. You may have seen it before. It's just from 2 years ago in Progress in Nuclear Magnetic Resonance. Another source that I would mention is an article by Lyndon Elmsley in a book published by Wiley that Tatiana Polanova and I edited. There's a nice overview, especially of relaxation measurements in that article by Lyndon Elmsley. And I think those are the two main places I was sending. So Art, I told them, we don't have overall tumbling, and anisotropy is a big opportunity. And I showed them lots of examples, and I think your timing is exquisite. I'm sort of done with what I wanted to say. Yeah, please.
Can I ask a question?
Of course you can.
Maybe it's a bit trivial, but
That'd be great.
What about REX contributions in solid state? Because
No, that's not trivial. That's so complicated, but we want to talk about that. We want to talk about that.
Yeah, I hear people claiming that you can do everything with solid state, like all dynamics, but then again, I think then it sounds to me strange that these type of motions would function in solid state, right? Because they simply require the interaction with liquid water, right?
Most of the I can't say anything that's true about each and every solid state sample from every lab. It's kind of like saying what are people in New York City like. But most of us try to keep things fully hydrated. So I think it's more a question of excursions and the displaced volume. So if you're in a crystal or you're really crowded suspension of liposomes, can you make excursions? Do you have available free volume? So it is about the solvent, but it's a little different than just saying there isn't the water.
So the hydrated, that's basically that's what the question was now towards.
There would always be hydrated. Gary Drobny showed a long time ago using nucleic acids that if you start to reduce the water from fully hydrated, that you shut down intermediate exchange so fast. They're beautiful studies from like the late 80s and the early 90s. So the hydration is important, but I think most of us are keeping things. You know, you can measure hydration by an equilibrium exchange with another solution, kind of like how crystallographers grow their crystals. And most of us could say that we're well over 95% hydrated, so that should be okay, except for this volume problem that we have a terrible habit of using every bit of our rotor to put another protein molecule in. That is actually a potential issue. Nevertheless, we started studying these exchange contributions many years ago. Tim data I was showing you, in microcrystals and other solids. Why? Because I knew that Russians had shown years ago that the enzymes are fully active. So I either knew that all those motions are happening, or maybe I would have a filter for the important motions, and maybe some stupid motions have been shut down.
Or there'd be no motions at all.
No, because the enzymes are functioning, and I don't accept the hypothesis that the enzymes. So they're faster, they're slightly faster. This was also in that literature, and we reproduced for 3 enzymes that the total throughput is much higher, usually, in the crystal than in solution. And so one has to assume that there's going to be motion there that accompanies a catalysis. That's not to say that all the motions that happen is there. It isn't just a funny thing from some Russian paper from the 1950s. There are also companies that sell cross-linked crystals to do chemical transformations, either for synthesis or actually to compensate metabolic insufficiencies for certain inherited diseases. So there's several companies that do that. They not only crystallize the thing, they cross-link it in place, and it's a brilliant enzyme. So from that, you know that at least for some packing forms, some crystals are fully active. We don't have any doubt about this.
Just by name.
Yeah.
view of
Right.
maybe the hydration. But so if it's not tumbling, hydration means a little bit hydrated, right? So some.
Why is it only a little bit hydrated?
So like some water molecules around it, right? Just.
This is my. So, well, I'm claiming that 98 or 95% hydrated is fully hydrated. It's not a little bit hydrated.
That means a shell.
Remember that a protein crystal is a lot of water in it.
It's about half water, and as are our samples. They're about half water.
But I mean, like loop motions, would they be the same? I mean, because
In our case, it was faster. And you could explain that in an empty simulation, which I don't know if you should believe or not, but the rate constant for some states, all states, was comparable to what we could get from solution measurements, whether it was T-jump or whether it was comparison to solution NMR, always comparable, and if anything, slightly faster.
So for example, if we have two domains which move compared to each other, would that be similar almost to tumbling? If tumbling doesn't happen, then
Now, this is what I'm saying. You have an occluded or an displaced volume issue to think about. So if the displaced volume is available space in that crystal habit, then there's no reason to think that it won't happen. Now, how could it be faster in the solid? We thought that there was a stabilizing interaction, which really it was a population effect.
so it's really it's comparable to just what crystallography happens. But because it's the same.
Well, I measured in crystals for which we have the crystal structure. But, so if you have, this is the way I would say it, if you have a motion that you're interested in studying and the displaced volume is either small or corresponds to a space that's a solvent channel,
Right.
then you're not expecting a problem.
Okay.
If the displaced volume is large and or occluded by a crystal contact, then we're expecting a problem. And sometimes the populations are different because of stabilizing contacts. So they can be different in a non-intuitive way. It could be apparently a higher value of REX just because the populations are closer to 50-50 or something. Does that make sense?
Yes, totally. Thank you.
Sorry, I wasn't clear the first time.
No,
Yes.
it was just.
But in terms of those motions and how you probe them by solids NMR, I'm hoping we have space in this class to talk about it. That's a lecture that's coming up. But Art's going to talk about CPMG and R1 row first, and then I'll talk about it.
If it's so much about the volumes, I mean, just as long as I'm still trying to fix this mic. So if it's so much about volumes, would probably have like motions which also like depend on pressure, whose existence depend on pressure would probably be a problem for a solid state.
There is a strong dependence on pressure for some motions, and I don't think we're in that
there's
range.
volume involved, right?
Yeah. But
When there's pressure.
my answer to that is sort of the same. It's case by case. Sometimes you have that volume, sometimes you don't. You know, so for some particular cases, and you could now look ahead and look at your crystal structure and know that. But up till now, it was a little opportunistic and lucky, I have to say, some of the things that we were studying. That we didn't fully know that this volume issue wouldn't be a problem until we got pretty far into the problem.
Okay.
And then I don't know if that's what you were asking about, but there can be other effects as well because of is the pressure well defined and all those kinds of things. I don't think that's what you were asking. You're just really asking about volume.
Yeah, maybe.
So there's no guarantee. There's no guarantee a priori that it's going to be the same as solution. And I think that points you to the opportunity just to take a larger view for a minute. In solution, you may see motions that wouldn't occur if that module were in the complete context that it functions in. Like one of the cases we studied by crystallography and by some NMRs, of course, is the famous molecule ubiquitin. And we found this other conformer, and we looked through the protein data bank, and we realized that conformer exists. It was there all along, but you only see it when it's on the de-ubiquitinating enzyme. So artificially in solution, you could say you're stabilizing one conformer when in complex with an enzyme, you stabilize another, and it just happens that for solids NMR, you're mimicking that other binding site. What do you learn from that? That probably our opportunity was to study those complexes. To study complexes where, yeah, it's occluded, but it's occluded on the functional pathway. And these studies of small systems by, crystallized materials and all that is just really just a training step to get there, I think in the long run. You know, this is a way to get the tools running and validating things. And the opportunity in the long run will be to look at those larger complexes, a small label module in the context of a larger hiding surface that is actually interesting instead of just a crystal context, right?
Okay, so what we're going to do today then is start to introduce chemical exchange, since Tom has brought it up. And then we'll come back to it in the solid state. And there's already a typo on the first slide that should say pulse length less than 100 microseconds, not milliseconds. So if we're looking at hard pulses, we frequently ignore.
No, it belongs to Mike. So, thanks. Sorry. I'm good.
Okay. Now we might have lost, if someone's listening, we might have lost, I think we've lost the GoToMeeting video, but I'm recording it so Mike will post it. I'll send it to Mike if somebody is online. So if we're analyzing relaxation in a pulse sequence, frequently we ignore relaxation during the hard pulses and just would add relaxation in during the delays. But of course, we might have long, weak pulses, so selective pulses, toxies, rosies, and R1 rho, where we actually have to worry then about relaxation during pulses. So just to remind you of the frame of reference and the rotating frame, and the various definitions of the tilt angle, the effective field, etc. This is a slide that occurred earlier, way earlier in the course, probably the very first lecture. So now the Hamiltonian, and actually, I lied, the beginning of this lecture is still fast time scale processes, but now with an RF field turned on, then we'll get to exchange. So now we have omega naught, the Zeeman effect, but we also have omega 1. So we want to get to an interaction frame where we remove both the effects of omega naught and the effects of omega 1, so we just have the fluctuating field. And that's normally done in 2 steps. So first we transform into the usual rotating frame. And in contrast to our first treatment, where we rotated at the frequency omega naught, so that the effect of the Zeeman term and chemical shift disappeared, now the rotating frame is at a frequency omega RF. That makes the RF Hamiltonian look time independent, but now we still have the residual offset, capital omega. And now we'll transform to the tilted frame, which will be indicated by primes. And we define the z-axis of the tilted frame to be along the direction of the effective field, which is V sub r in this picture. So I go through and do this transformation and do a little bit of algebra. And now have an effective field, omega E, pointing along the z-axis, and then the fluctuating field is shown here that has components along the z prime axis and the x prime axis. The part that is dependent on the fluctuating field I call H1. I put a prime on to remind us that this is in the tilted frame. And that has, I can express this using the tensor components to get back to our old language, in which I've defined now the tensors using B's rather than A's. I forget why I use B's. and now transform that into the interaction frame, I need to get rid of omega e. Right? I still have a Hamiltonian that contains this term. I want to get to a frame where I only have the fluctuating term. So to get rid of this, I have to rotate around the z prime axis at a frequency omega e. And then I have to transform, right? I have to transform the operators, and again, I pick them so that in the new interaction frame, they just pick up the phase factor that goes by omega e times t. So this parallels what we did before, except that we have this we have this two-step process where we have to get into the tilted frame first, and then we can do the rotation to get rid of omega e. There's one tricky bit here. In some cases, we might have to worry whether in the presence of the spin lock field, we've made some operator terms degenerate, and therefore secular, that weren't secular before. That mostly comes up in homonuclear cases, not heteronuclear cases. And an example that could be, for example, if the spin lock field was strong enough, then to a good approximation, the homonuclear zero quantum terms might become secular with the ZZ terms. But if we're talking about heteronuclei, that really doesn't come up. But then our result looks the same. We just have, for example, what's called R1 rho is the relaxation rate constant for magnetization along the Z prime axis. And we have the same kind of double commutator. It's just our new operators are here. And there'll be new frequencies here. The omega q's will be whatever the frequencies were of our operators B sub 1 and so forth. But there's nothing new in the formalism. It's the same kind of spectral density function, the same double commutators. It's just different operators. And if we work this all out, we end up then with R1 rho being 2 times the spectral density, now the frequency omega e, rather than omega naught or omega 1. And if I plug in for the f's, I get something that looks very similar. There's this fluctuating field along z, but we pick up a sine squared theta term, and that came from here. In my new tilted frame, the f's had a sine squared theta dependence because the fluctuations along z didn't point along z prime. They had to be projected onto z prime. And I got this sine component. So these are all kind of algebraic details. And we end up then, if we had a single exponential decay with single exponential process with rate constant k, we end up with this expression for R1 rho. And then if it's a two-state jump process, we end up with this famous result. The fast limit R1 rho has this functional form for a two-state jump, where PA and PB are the populations, and KEX, again, is the sum of the forward and reverse rate constant. All right, that's a little bit of an aside. So we said that the condition for the fast limit was this. And when this is violated, I've told you multiple times that the Taylor series no longer works. So we need to do something different. What are called the Bloch-McConnell or stochastic Liouville equations are what one usually turns to. And we'll do this in the context of a chemical reaction. So suppose we have a reaction as shown here. A plus C goes to B plus D. The first very useful simplification is, of course, a nuclear spin can only be in one molecule at a time. So if we are monitoring a spin in molecule A, after the reaction, it's either in B or it's in D. We can't split, say, a carbon-13 in half and put half of it in A and half of it in D. So that's a really fantastic simplification because it means we can always define pseudo first-order processes. So here I've assumed that the spin of interest is in reactant A and product B. And then C and D, just let me define these pseudo first-order rate constants. They're invisible to the NMR experiment. And if instead the product, the spin ended up in C at the end, it would just be B would be defining the pseudo first-order rate constant. And if I had more reactants and products, it all reduces back down to a pseudo first-order equation because if I had A plus C plus E goes to B plus D plus F, I would end up with the same sort of thing, more first-order pseudo first-order rate constants, because again, the spin can only be in one product molecule and one reactant molecule. If we just wrote chemical kinetics, forget about NMR, if you just wrote down chemical kinetics rate laws, you would end up with rate laws that look like this. And I brought the primes here. You just know that these are all pseudo first-order rate constants if need be from here on out. But that's just chemical kinetics. For future, I think I showed you this before, if we calculate the eigenvalues of the rate matrix, we get 0 and KEX. So the Bloch-McConnell equations say that we can just add in the kinetic equations into our normal NMR Bloch equations. So now for Z magnetization, we say that species A has its own R1, species B has its own R1, but then magnetization is exchanged between A and B by the rate constants. And that's the end of the story. If I had more than 2 states and I wanted to know about R1 relaxation, I just expand the rate matrix. I have a column vector with however many states I need, and then an exchange matrix with as many kinetic equations as I need. But this has in it a very important assumption, but it's a very good assumption. And that is, when the reaction runs, if I start with Z magnetization in the A state, after the reaction, I have Z magnetization in the B state. I don't have X magnetization after the reaction, or Y magnetization, or double quantum coherence. That all that happens is we swap the labels. So the frequencies change, the coupling constants might change, but whatever coherence state we're talking about doesn't change. So the chemical reaction doesn't turn Z magnetization into X magnetization, or the chemical reaction can't change in-phase magnetization to antiphase magnetization.
I mean, it's instantaneous phase, it has to be identical.
And
But
then,
the speed is not continuous.
and then we also think that the reactions are, the transition over the barrier is very fast. So the lifetime, you imagine the chemical reaction, goes over the activation barrier in order of bond vibrations or femtoseconds. So if the reaction is slow, it's not slow because you ooze over the barrier. It's because you spend most of your time waiting in the bottom of the well until there's a random fluctuation that provides enough energy to jump the barrier. And then you rattle around over here. So slow rate constants mean long lifetimes in a state, but the transitions over the barrier are fast. And if the transitions over the barrier are fast, that means two things. One, there's not enough time for the coherent state to change from Z magnetization to X magnetization. And, as Ann said, the phase is continuous during the jump. So if we've had transverse magnetization and some bit of transverse magnetization has processed at some frequency omega A and has acquired a phase phi 1, after the jump, it still has phase phi 1, but from then on it will start to process at its new frequency omega B. So instantaneously during a jump, the phase is maintained. So those two assumptions make the problem much easier to solve than it otherwise would be. So we can just keep doing this for multiple states, turn it into a matrix equation, solve the matrix equation in Mathematica, so on and so forth. So here are just some examples then for Z magnetization. That here is just inversion recovery if there was no chemical exchange. And now, if there is the chemical reaction happening, and we invert one of the spins selectively, then we start to see magnetization transfer to the other spin, and then eventually they both decay. So that looks a lot like an NOE experiment, except it's driven by chemical exchange between sites rather than the nuclear Overhauser effect. And in fact, in a NOESY spectrum, chemical exchange cross peaks look exactly like NOE cross peaks. And sometimes people have a hard time figuring out, are they looking at an NOE cross peak or a chemical exchange cross peak? So for Z magnetization, that's pretty much the end of the story. One just solves that matrix equation and plots the results. This leads to very powerful experiments called Z-Z exchange experiments or exchange experiments for homonuclear cases, because if the process is slower than the R1, slower than the T1, then we can measure the kinetics by analyzing the shape of these curves. I think next lecture we'll see some examples of that. But probably more interesting, actually, is what happens with transverse magnetization. Again, we can add in to just the block equations now the effects of exchange between sites. So each site has a chemical shift in its own R2, but now they're exchanging with K1. We can solve them. A brute force approach, if you want to know what the spectrum is, the brute force approach is to integrate this equation and then Fourier transform it, and then add up the two signals. If you actually care about the frequency spectrum, there's a more elegant way of doing it. I'm just going to click through this quickly. You can look at it. If we have a matrix, write this as a matrix equation, then we can do the Laplace transform rather than the Fourier transform. And the Laplace transform has a derivative property in which the Laplace transform of the derivative is equal to S, the transformation variable, times the Laplace transform of the function, minus the value of the function at time 0. So that lets us convert the differential equation into an algebraic equation. And we can solve the algebraic equation, as shown here, and then we have to understand the notation is a little sloppy here. This should really be S times an identity matrix with the same dimension as R. Otherwise, this equation doesn't make sense. And then we make the trick that we really want to know the frequencies. We're interested in the frequency spectrum. So I just substitute S by I omega. And this gives me the NMR spectrum without having to do any more transformations, etc. So I just have to sum up the columns shown there. So here's an example of doing that. That's mostly useful if you have to calculate lots of spectrum. Computers are so fast now that integrating the differential equation and then Fourier transforming is still fast if you only have to do a few calculations. But if you needed to do lots of these calculations, it's way more efficient to do the Laplace transform, which is why I showed it to you. And here's just some examples then of changing the time scale of the jumps. And this is to make the point now. So here was the spectrum in blue when there was no jump. And now orange, I guess that's orange over here. The jumps are slow. The lines start to broaden. Green, the line is very broad, and you can see the line has pretty much disappeared over here. And then red and blue start to come into the fast limit. Right? The fast limit, we said we had an averaged resonance line. So this would be where the red field approach works. Outside of this range, then the red field approach won't give us the right answer. And this just shows the same thing. Actually, let's go back to this equation. Here, we know two limits. If exchange was fast, so that the resonance lines collapsed into a single resonance line, then we know we can calculate at least an adiabatic part of relaxation from variance times correlation time. So we just have to calculate the variance in the chemical shift and multiply it by the correlation time. The only time constant is 1 over kpx, because that's the only eigenvalue that is not 0. So in the fast limit, we know the answer, variance times correlation time. What about the slow limit? Suppose exchange was slow to where we see two resolved lines in the spectrum. What's the broadening due to the jump process in that limit? If we had two resolved lines, what would I say about those coherences? I told you there was only two important things about relaxation. One was the variance times correlation time, and then what was the other? The secular hypothesis, right? So if we have two, if the lines are resolved, are they secular or non-secular? There's one vote for secular if they're resolved. Anybody want to vote for non-secular? If they're resolved, we say they're non-secular. And if they're non-secular, can they cross-relax? No. So in that limit, in the slow limit, if there's two resolved lines in the spectrum, they can't cross-relax. So I can set the off-diagonal terms to 0. And then I can just read off what the broadening is. The broadening of the A site is by K12, and the broadening of the B site is by K21. So I know the two limits. The fast limit is variance times time, and the slow limit is just the jump rate out of that site. And that's easy to understand why that has to be true in the slow limit. In the slow limit, the lines are resolved. So the two magnetization components are acquiring a phase difference. And now say the red, some bit of red magnetization jumps to the other site. It starts to acquire phase relative to the A site. Now it's in the B site. When there's a random jump back, it could have any phase at all, right? Depending on how long it stayed in the B site. So the jumps back will end up having phase around 2 pi and can't contribute to the signal. So there's only loss in that case due to the jumps out. Where in the fast limit, the jumping back and forth is happening before a phase difference can accrue. That's the major difference, right? We said in the fast limit meant that we didn't accrue a phase difference, and we can't tell the two lines apart. So the jumps back and forth aren't accruing this 2 pi phase difference. So there's different behavior than there is here. Here, in the slow limit, there's only loss. The jumps back are incoherent relative to the jumps out.
It might be interesting to say that when you're in that limit, but not fully in that limit. You know, people talk about being in the slow limit or the fast limit, and sometimes we're not that careful about saying how many orders of magnitude faster or slower. So you're kind of in the limit, but not that close. You do get oddly phased spectra, yes, strange line shapes, broad peaks, and it's a nice thing to be aware of because it's very diagnostic. It can happen to be able to detect it if you're lucky enough that your process is just at the right time. But it wouldn't be covered by any of these limiting.
Right, so in here, when you get into this regime, the line shapes can be not purely Lorentzian, and in fact, I mean, there still is another line somewhere. It's just that this singleton noise, you don't see it.
Very right. And these all look pure phase, but they don't have to be.
They don't have to be pure phase.
You can have a pathological case where it wasn't even phase. And sometimes we've been accidentally lucky that we're right in that regime, and the student lost all his time thinking that she didn't know how to phase, and that wasn't the problem. It was actually really interesting line shape.
If the populations aren't equal, then K1 and K minus 1 aren't the same size, or K forward and K reverse. So if the A state is overpopulated relative to the B state, the reverse K is larger, and that means that the smaller population line is broader in the slow limit. And you can almost see that here. This line has come down by not quite a factor of 2, and this line has come down by more than a factor of 2. So that makes it doubly hard to find the minor state. If the minor state has a population of 0.1%, the jump rate out of that state is going to be roughly 10 times larger than the major state. So you have a line whose integrated intensity is 0.1, and its line width is 10 times bigger. So it's a very short line that's very broad. So the minor states very quickly become impossible to find in a usual solution in a Lyric spectrum. because of that effect. Yeah.
I mean, in the practice of doing any experiments, any case where the limit is not, where we are not in the slow enough limit and fast enough limit, call it fast or slow, the peaks, apart from a minor peak, wouldn't be really visible anyway, right?
That's not true. That's been done on proteins.
What, I didn't hear what you just said.
So I mean, the green case, for example,
Yeah.
that's not really something we would really detect.
Well, it depends. Right? I mean, it's all a matter of signal to noise. These sorts of line shapes in the middle become very sensitive to the populations and timescales. So sometimes they're broadened away, but sometimes you can find them. It depends.
I don't think it's a favorable case for sensitivity, but that's one of the things we did on the tin blue in solution. Just detect the line shape because we were so lucky that it was exactly on that time scale, and you get distortions in the line shape that are concentration dependent and temperature dependent. It's a very old-fashioned idea. You know, it doesn't have any of the elegance of all these modern experiments, but it was a lot of constraints that came out of it.
And actually, if you're looking at if the kinetic process was binding of a small molecule to a protein, then you could be, the small molecule could be in the limit where there's substantial broadening, but you still have enough signal to noise to measure that. So there was a really nice one. Tanya Mittag was a graduate student. She did a lot of such studies. And then being in this kind of middle regime is the most informative regime. Because over here, all you learn about is variance times time scale, and over here, when you're in the slow limit, all you learn is the jump rate. So being in the middle, if you can find the signals, tends to be the most informative.
Question, if you go back to this, just this kinetics equation in the block, you were pointing out how this is going to affect secular versus non-secular. So I wonder if you ever get a case, you know, at first glance, it seems like, oh, this is cool, you're going to tease out K12 instead of the sum of them. And then you realize, well, most of the time that you could actually do that, you already have the populations from the peak heights, so maybe it's redundant information. If you think of a situation where you have more sites, is it always the case that having separated the rate constants is redundant information? Like a 3 site or a 4 site. Now you pull just one rate constant out in a privileged way. You're trying to ask whether there's a missing state you didn't catch, or it's always useful, you know, most of the time we're studying the sum of forward and reverse, and we don't have the opportunity to accurately pick up just one or the other. I guess for that to be useful, you have to be able to carry a system through a broad range, where it will go into fast exchange and slow exchange. That's what's really not going to happen.
So titrations, the ability to titrate something is really helpful.
Of course, yeah. We haven't done anything without that.
Sometimes temperature is the titrant, because if you have more than one state and you have different activation energies, changing the temperature around can help shift shift the time scale of one versus the other. In principle, I don't know of a case where it's been done for 3 states. In principle, you have the ability to be lucky if you think, no, we've done 3 state with temperature.
But it is a new piece of information. It isn't giving you the same information that the population is. Let's say you had 3 states.
But for the populations, we still don't get the sum. I mean,
Yeah,
you just get the ratio, right? So it's always useful, isn't it?
I think it is. I think that's right. It's a new piece of information.
But I was going to say, I don't think it's been used in a 3-state case, but in principle too, you can shift around what regime you're in by switching to the 0 and double quantum coherence, because now you depend on the sum and difference frequencies rather than the absolute differences. So instead of delta and omega, say for the carbon, you would then be the sum or difference of delta omega for the carbon plus delta omega for the hydrogen. And there's some possibility there of shifting the relative timescales for the different exchange processes.
Yes.
I mean, anything which changes these timescales, whether it's meaningful or not, is useful, right? So as long as the more we can rationalize it, the nicer.
Yes.
The more we can rationalize it, the nicer, right? But in principle, anything can, especially.
So these then are the two limits. In slow exchange, you just have the jump rates. And in fast exchange, we have variance times correlation time. So correlation time is 1 over KEX. And this turns out to be the variance in the chemical shift for the two-site jump, which you can work out if you want. Sometimes you'll see in the literature that P1, P2 delta omega squared is called phi EX. And phi EX has nothing to do with variance in the mathematics literature. But the first paper I wrote about this was before I realized that that was just the variance in the chemical shift. So I was just trying to think of Greek symbols, Greek letters, so I called it phi, and now everybody calls it phi, which would have been better to, of course, call it sigma exchange squared, because sigma is the standard deviation, so sigma squared is the variance. There's not a mathematical symbol just for the variance, but it's too late to change, and maybe it's okay because introducing one more sigma when NMR is already full of sigmas may have been more confusing than phi. But I'm always a little embarrassed when I see phi EX. Well, here's what I just said about multiple quantum relaxation, because now the double quantum delta omega is the sum of the individual delta omegas, and zero quantum is the difference between the two. And otherwise, the equations are all the same, but you have some ability then to change the time scale. For example, if it happened that these two deltas were of the same magnitude but different sign, the double quantum spectrum would narrow because you'd have the difference of two numbers, and the zero quantum would broaden. And Pervushin showed this after he did the dipole CSA trozy. He showed that there was a chemical exchange trozy. You have to be a little bit lucky because you have to have the shifts of the two nuclei roughly balance each other. I usually think that this should be useful in protein folding studies because the secondary shift for the C alphas, for example, going from random coil to helix, is about 4 parts per million. And for the H alpha, it's about 1 part per million. But in absolute units, that's the same, because the Joule-magnetic ratio is 4 times larger for the hydrogen. So it always seems to me that we ought to have strong protein folding, in protein folding studies, there ought to be strong effects on zero and double quantum spectrum, but we haven't made that work yet. And if we had triple quantum spectra, then the broadening would depend on the sum of 3 delta omegas. And you might imagine some case in which the single quantum spectrum was very broad, the double quantum spectrum was very broad, but the triple quantum spectrum was narrow by accidental cancellation. And that turns out to be true in VPTI. And Vutrich's group was, in the early days, reporting homonuclear spectra of ubiquitin, right? As soon as they invented a new 2D experiment, they reported on ubiquitin, on VPTI. They were doing assignments, and then one day somebody records a 3 quantum spectrum, and a new resonance line appeared, a very strong, sharp line appeared with shifts that made no sense to them. They'd never seen any signals with the shifts for that particular, would add up to that triple quantum signal. And this turned out to be the case. It turned out that the lines were broadened to oblivion in the single quantum cozy. They were broadened in the double quantum spectrum, but in the triple quantum spectrum, they happened to add up to 0 and give a very sharp line. And it was Mark Rance who explained it. So he has a JAX communication from a long time ago showing that this triple quantum spectrum happened to be a case where chemical exchange for 3 different spins added up to 0. So it was a Trozy experiment 2 decades before anybody had thought of Trozy experiments. So here's just some sample calculations, for example, of the function of, for some fixed value of delta omega I, you can find frequencies where you would narrow the double quantum spectrum or narrow the single quantum spectrum, and also frequencies where you would broaden them all. So sometimes people talk about multiple quantum chemical exchange as if it's very complicated, but it's not. It's just that now you have the sum of the individual delta omegas. So over the last, so it's fine, we can measure line shapes. So for many, many years, measuring line shapes, as Anne said, was a very powerful approach. Particularly in small organic molecules, large numbers of chemical reactions in organic chemistry were characterized by measuring line shapes in NMR. But these days, a lot of experimentation is done in which relaxation is measured while perturbing the spin system, rather than just letting the spin system evolve. And one example is the Carper-Cell-Nebel-McGill experiment, in which we have a block of spin echoes that's repeated over and over again. So this block of 2 spin echoes would be repeated some number of times, so that if we have free precession, now the solution to our differential equation during a given value of tau CP would be just this matrix exponential, the shifts, the relaxation rate constants, and the kinetic matrix. And if we do it a bunch of times, we end up with this equation, in which star means complex conjugate, and that reflects the fact that a perfect 180 just changes the signs of the chemical shifts. Right? The shifts come out and the shifts come back. So this then would represent evolution through m blocks of the CPMG cycle. And hopefully, one can then define formally a relaxation rate constant just by doing what you would normally do. You see some decay, you take the logarithm of the decay, divide by the time in order to get an effective rate constant. And then in the experiment, we do this over and over again, varying the pulse spacing. And that's called the dispersion curve. There's some theoretical results for 2-state exchange and also in the fast limit. But here's just some long ago data. So here is the pulsing time, the time between 180s, or actually this is half the time between 180s. And the rate is measured. So when there's slow pulsing, we see the full broadening of the signal. But then as the pulsing rate gets faster, the broadening goes away, essentially because the chemical shifts are being refocused faster than the jump rate. This is what we talked about in the beginning of relaxation. This plateau represents the relaxation due to tumbling. We can't pulse fast enough to get rid of the relaxation due to random tumbling, only due to the jump process. So the fact that we see dispersion at all, a dependence on the pulsing rate, says that there's some process in the molecule on a time scale similar to the pulsing rate. So when the pulsing rate is slow, the process is active in causing broadening. And when the pulsing rate is fast, we've suppressed that contribution from broadening. And now, let me see what's next. I wanted to show you a picture that I haven't put in yet. And so, this picture you've seen before. This was right. This is just a picture showing dephasing of different sub-ensembles of magnetization. And if we add together a few thousand of them, we get the blue curve that looks like the free induction decay, and then some damping due to transverse relaxation that's now drawn as the black line. Right? But now, what I'm going to do is the same thing, except periodically there's going to be a 180-degree pulse applied. So what's going to happen? The different spin components are going to start to dephase, but then there's going to be a pulse that will cause them to try to come back together. And but the random jumps are still happening. It's the same simulation that you just saw, just with 180-degree pulses every so often. And now, you can see these didn't dephase completely the way they did over here, or as completely. The yellow line up there, which was the sum of 1,000 components, has barely decayed at all. Or the yellow line is the sum of these components, it's barely decayed. The blue line is now the sum of 1,000 components. It's decaying, but it's decaying much more slowly than the black line, which was the curve from the simulation without the 180-degree pulses. So the constant refocusing has kept the magnetization from decaying away as fast as it normally would. So that's basically how the experiment works. And if the delay is too long, the magnetization all dephases, and then that's the end of the story. So if the pulses are very far apart, we would see the black curve, and as we make the pulses closer and closer together, we see the blue curve, and the limit is really set by how short the pulses are, the 180-degree pulses. Normally, again, we want to ignore what goes on during the pulse and only think about the delay. So at a practical level, that means generally we want the delays to be about 10 times longer than the pulses. That just seems like a good heuristic that if the duty cycle is only about 10%, maybe we don't have to worry about what goes on in the pulses. There's not really much theory or calculations that anyone has done about that. But it just seems like it's a rough heuristic. So that means on a solution machine for nitrogen-15, a 180-degree pulse is maybe 50 microseconds. And if we apply this factor of 10, then we would say we could pulse as fast as every half millisecond. So the processes, and then we can obviously pulse more slowly. So processes that are on a time scale order a half millisecond or slower, we might hope that we can do this experiment on and then characterize timescales. So go back to here, that's what's done. And the data is fit with theoretical expressions due to Carver and Richards, a paper from the 60s, for 2 states. It also turns out to be important in these experiments to obtain data at least 2 magnetic fields. That turns out to be critical because of this result. So in slow exchange, how does the broadening depend on the size of the magnetic field? It doesn't, right? It's just the jump rate. So in slow exchange, the amount of broadening is independent of the size magnet. Here's the fast exchange result. How does this depend on the size of the magnet? Delta omega is proportional to the magnetic field. So here we depend quadratically on the size of the magnetic field. So the magnetic field dependence helps figure out where we are between fast and slow exchange. So if we look at these data, here's a case where there's a large dependence on the magnetic field. This is data at 500 and 600. You can see here at slow pulsing, there's a large dependence on the size of the field, and that means we're close to the fast exchange limit. Over here, there's almost no dependence on the size of the magnetic field, and that means this system has gotten close to the slow exchange limit. And these are different temperatures, so we can kind of shift things around a little bit with respect to temperature. But if we had data at only one magnetic field here, we could almost certainly fit it with an equation that would look like we were in fast exchange. The only sign at a given field that we're not quite in fast exchange, you can see there's a little bit of a kink in the curve here. But without that second field, that kink wouldn't appear. We could just fit something smooth like that. It's really the inability in the fast limit, we could never account for how small this difference is. We almost missed that because we just originally had data at one field, and when we just had the data at one field and we were looking at this residue, and we couldn't decide, we were having a hard time deciding whether we thought this point, which seemed a little bit weird, was correct or not, or whether there just was a problem at long pulsing times. And it was only when we got the data at the second field that we realized what was going on.
So can I ask a question, even though I missed some important things you said? The features in the dispersion curves here, these are fits to the equation. These are not just smooth lines through the curves.
Right, those are fits.
And the feature in the fit has what almost looks like a turning point. And can you say something about what it tells you about the model? Where that
I can't, but Hans can. So like here.
Art is pointing at, he understood my question. Right there, you have a pretty abrupt change in slope.
He's now the world
I
expert.
mean, you mean the black curve, or do you mean the
fit.
plateau?
Yeah, the fit changes from a sort of plateau regime to a log linear descent at a pretty sharp point. And what is that? What is the position of that point that's teaching us about the fit that underlies that simulation?
I mean, it's not so easy. Let me think about it.
It always is so funny to me. It almost looks like a mistake when I look at
Because
some of the works.
I've played with it quite a bit. it can be so this is
So for two
So-
states like this, when exchange gets slow, what you're really looking at is 1 minus sine squared, and 1 minus sinc. So really you should think of it as going this way, and what you're seeing are the sinc wiggles. If you imagine that a sinc function would look like this, and what we're looking at is really 1 minus the sinc function normalized in some way.
Yeah.
So you're seeing this go that way. You're just seeing
I mean,
the
we can still
beginning
not,
of those ripples.
but we can still not really say why it's there and what specifically it is, right? I mean,
Right.
It
I
is
think
more
Lewis-
sensitive to some
But I
parameters than
think,
others.
but I think Lewis is published a paper on how exactly this happens. I mean, what actually the oscillations in the beginning mean. Is it what you?
Right,
I mean,
so
to
that,
rationalize what really happens with magnetization can be explained why this goes up and down so strangely, why there are these
Or what parameters are in that frequency, what parameters are in the
So,
position of the turning point. It must
I mean,
be
I have-
sensitive to different things.
what I have done, so I haven't really looked at this particular thing, but what we are trying to get out is some work on looking at the relevance of the early and late part of the curve in terms of contributions to exchange between minor sites and major and minor site in three-state systems. So these curves can tell us something. So like the early part of the curve in a three-state exchange system would tell us about the exchange between the major site and the minor site, while the tail of the curve, like the large 1 divided by tau CP, would tell us about the exchange between the minor sites. So if you have a ABC scheme, and if B and C are minor sites, and there's exchange between those, that would, for example, affect the later part of the curve. So,
But it also comes up just in the two-state.
well, but in the two-state, of course, we don't have any minor sites, so
Right.
I'm really worried
It's
about it.
interesting that you can separate any information. Well, maybe we
Well,
can
but
discuss it more.
that's maybe why it's good to have approximations where you can look at the equation. But I think in that case, the sinc wiggles, what it means, it's really also an experimental issue, right? Because of the
Right, so in very slow exchange, the sinc wiggles are when the pulsing rate is
Right.
matched to the jump rate. If you get to very slow exchange.
It's pretty neat that that happens. It's not a very deep modulation, but it's still neat that it happens at all.
And
but the key there, right? I mean, why the key is there, we cannot say that, right? Right now. So we cannot like anything qualitative if you see the kink being later or earlier, what it means.
no, I'm not thought about it, not thought about it.
You have not?
No.
Yeah. I mean, I can try to think about it someday.
I'd be interested.
So so that's the CPMG experiment, a series of 180-degree pulses. But we run into trouble when the delay gets short. So to get the faster timescale processes, we would like to be able to pulse even faster. And we can't pulse faster. So then we switch over to an R1 row experiment. So this just reproduces where we started. Here's the differential equation, again written in matrix form. And we know how to solve this in the fast limit. Right? In the fast limit, we would just do the Redfield equations just like we did in the very beginning of the class. But what should we do if we're not in the fast limit? Here's this more stuff about the equation, about the matrices, that's boring. Here's an example. Then we get to very large matrices quickly because we have to keep track of, for each state, X, Y, and Z magnetization. So the CPMG, we can just keep track of M plus. But now in R1 row, when we turn on the RF field, magnetization would be rotated around the RF field. So we have to keep track of X, Y, and Z magnetization in every state. So if we have 2 states, we end up with a 6x6 matrix. If we had 3 states, it would be a 9x9 matrix. So the dimensionality of the matrices get to be very large very quickly. And a 6x6 matrix doesn't have any analytical solution except in special cases.
This kind of is a special case.
Yeah, but it's not special enough. So we, of course, always could solve this numerically. But then there are some approximations we can make. So as I already said, R1 rho is the relaxation rate of magnetization locked along the Z prime direction. Orthogonal to that would be R2 rho. And R2 rho decays away very quickly. R2 rho tends to be very large. Plus, in the magnetization that's orthogonal to the spin locking field tends to dephase from B1 inhomogeneity, unless you do something like apply a Waltz decoupling field. But just in a CW field and a solution probe, magnetization orthogonal to the effective field tends to dephase. So that means we're most interested in R1 rho. That's the slowest decaying magnetization. And that means it's associated with the least negative eigenvalue of this equation. We have this big matrix equation. 6x6 means there's 6 eigenvalues. But we're only interested in the one that's closest to 0. All the big eigenvalues will just dephase. So we just want to approximate the least negative eigenvalue. And we had spent about a decade doing this by various methods, and then ended up with a very simple result, that the least negative eigenvalue is approximated by the trace of the inverse of the Bloch-McConnell matrix. What's the trace of a matrix? What does the trace mean? The sum of the diagonal elements. So we take the matrix of chemical shifts, relaxation rate constants, kinetic constants, calculate the inverse of that matrix, and then just sum up the diagonal elements. And it's very simple. So we have to worry about this projection into the tilted frame. So the projection into the tilted frame can be factored out in most circumstances to give these dependencies on the angle. So sine squared theta times the exchange broadening then is the negative of this eigenvalue that we can approximate. So on and so forth. And here is that first order result. Now, let's contrast that to what we got from Redfield theory. The Redfield theory result was that REX equals PA, PB, delta omega squared over omega E squared plus KEX squared. So this is fast limit. And this equation made no assumption about what time scale we were in. Suppose the populations were very skewed. If the populations are skewed so that the population of the B state is small, how does omega bar compare to omega A? Omega bar is the average chemical shift. Is it similar to omega A or very different to omega if the population of the A state is very large. They're similar. And in that case, omega E squared cancels omega A squared, and we end up approximately with the result PA, PB, delta omega squared over omega B squared plus KBM squared. Omega B is related to the chemical shift of the B state. And remember, way back here, in our simulation, the B state may be invisible to us. Remember, the B state is going to have an integrated intensity equal to PB, but its line width is proportional to K21. So this state may be completely invisible to us in the NMR spectrum, but R1 rho, the relaxation rate constant that we measure on the observed state, depends on the frequency offset to the B state. So what is it that we do? When will this term be maximized? This term will be maximized when the denominator is minimized, which will be when we're on resonance with the invisible state. So we can do the experiment measuring R1 rho for the observed state, shifting the frequency of the RF field, and when we find a maximum, that tells us the frequency of the minor population. In the fast limit, we only learn about the mean population. So it also turns out in the CPMG experiment, we only learn about the average chemical shift in delta omega. So this is something completely new. We can find an otherwise unobservable state by stepping the frequency and looking for a maximum in R1 rho. That has really made the R1 rho experiment popular. It's that property of R1 rho that we're sensitive to the offset of the minor state. So this just repeats it all here. And we can keep extending all of this mathematics. But here are some sample calculations. So I have to get myself oriented. So here the population is this top curve. Well, let's just look over here. The population of the B state is 0.1. We're looking at the relaxation of the A state, the state that we can see. And now the fast limit result is the orange curve. We're sitting right on the mean frequency. So the offset for the mean frequency is 0. But that's wrong. You can't even see. Behind the blue curve is a black curve. It's the exact calculation. And then the blue curve is the equation there. And the maximum is shifted away from the average position. We would say that's the chemical shift of the invisible state, the minor populated state. if the populations go up, right, then omega E and omega A start to become somewhat different from each other. We need a more accurate theory. So here, for example, this is the simple result, but then we have more complicated results that are accurate. Here, now we've made KEX 5,000 per second. So KEX is now 5 times larger than delta omega. Delta omega is 1,000. KEX is 5,000. We might have thought that was already in the fast exchange limit. This is Ann's question, how fast is fast? But even here, you can see that there's some difference. There's an offset from the mean frequency. And in fact, Hashim al-Hashimi a year or so ago showed that one can actually be fairly far into what you would think of as fast exchange and still tell the difference between these curves, letting you find the minor species, and the red field result. More curves. We can expand the matrices to all kinds of kinetic schemes and do these calculations. And then just, I think, to end, what about, say, coupled spin systems? Now we have, I've added in the coupling partners. There's just the chemical shift evolution. Now I have to include the J coupling as well as the chemical shift. But now, as I said, we rely on the fact that the transitions don't change one operator into another. They just change the labels. So that means oops, that was the end. That means, I really need to show you that. That means when I start to add in the kinetics, this term, this is the doublet component that is shifted by plus pi j. It can never jump over to this doublet component, which is shifted by minus pi j, because that would involve flipping the alpha state of the S spin to the beta state of the S spin. So when I build the matrix, this is always going to be a 0. The kinetic exchange can only be non-zero here. That takes the A state, the alpha state of the S spin in species A to the alpha state of state B. So this term can be non-zero, but this one has to be 0. The jumps can't change the spin states. They only move them from one environment to the other, where they have different frequencies, and they might have different relaxation rate constants, different R1s and R2s, but we can't mix up the different states. And that's a great simplification, because then I could treat it, I don't have to build this big matrix. I just have 2 separate problems. One for I plus S alpha turning into I plus S alpha on the beta state, and a separate problem in which the beta states jump between molecule A and molecule B. So I can always break down, if I think I have exchange in a coupled spin system, I can break it down into a bunch of subproblems. I don't have to solve this 4x4 matrix. I can solve 2 problems of dimension 2x2, one for each doublet component. And that's a terrific simplification. And that's where we'll end. sorry we ran over today by a lot, but
It was interesting.
that got us caught up.
Actually, the answer would be, I mean, it's a point is more so really the only it's not going to do with K, right? So this K is tau and
Yeah, give me 1 second. I'm gonna just totally screw something up. No, it's okay.
I mean, also this shit is not so obviously the omega is the omega right? That's only so that position does not show kx. So yeah, and that means in turn if you think of the single omega let's say it's a plot for C squared function. And we see that this point here is about pi. So that means this is normalized is actually, I mean, of course, it's 1 divided by tau. So basically, the point where this goes down, that is the omega, this
你
one,
是一个不收语件了吗？
tau equals pi.
不是说只有考过的人，没考过的人应该做到少一点。
One to determine the omega.
No, tell him that next time.
Yes. But I think this is, yeah, I think these are, maybe for some it's trivial because they know anyway. Not to.
Well, Matt and I switched now switching over the go-to meeting, so
Okay, so the go-to meeting for the halfway through.
yeah.
Okay, that's okay.
But then I recorded myself on my computer, so I'll send Mike
Okay.
the recording of me.
Okay.